is 0, so you know that that's when that's 3 minus x over what? In this case, negative 2, right? So what does that mean x equals? 3. All done for that section. Find the x-coordinate of the point of tangency. So is that the x-coordinate of the point of tangency? Yeah. To make a fraction equal to 0, what needs to be true? Done. And determine whether f has a local minimum or maximum or neither at that point. How do you figure out if a point is a local min or max? You have two different tests. They're called the something test and the something test. Second derivative test and the first derivative test. If it's increasing and then decreasing, it's a max. If it's decreasing then increasing, it's a min. If the second derivative is negative, it's a max. And if the second derivative is positive, it's a minimum. Which one do you want to use? First derivative test or second derivative test? Second derivative test, please. Let's do the one that's the least amount of work. Sound good? Okay. I mean, I think it is, and it's also good practice for us. So we know that dy dx is equal to 3 minus x over what? Y. Thank you for reading the question back to me. 3x over y. So we need to do the what derivative? The second derivative. We're doing the second derivative with respect to x. So what are we going to have to use here? What rule? We don't have to separate it. We're not integrating it. You only separate when you're integrating. We're differentiating here. So what are we doing? Implicit differentiation with what rule? Quotient rule. That's a quotient, and there's x and y. We're using implicit differentiation with the quotient rule. So it's going to be low times the derivative of the high minus high times the derivative of the low all over y squared. We want to know what the second derivative is when what is true? When x is equal to what? 3. And y is equal to? Negative 2. That's what we just did in the first part of this question. It's what we just did. So what's that going to be? Negative 2 times negative 1 minus 3 minus 3 times y. Oh, what is y prime? 0. No, y prime is right there. 3 minus x. It is 0 right here, so you don't actually have to plug it in. You're actually correct. In this case, it's going to be 0, but look, is it really, really 0? Look what we have here. We have y is negative 2 squared. This right here, that's 0 times 0, which is definitely going to be what? 0. So yeah, you can make that observation. You already know it's y prime is 0 there. But in this case, it's squared like this. So what's it going to be? 2 over 4, which is 1/2. Is that positive or negative? Positive. So concave what? Up. So what does that mean about? Is it a min or max? So min. Yep. That's what you need to do. The second derivative is by far the easier one to do in this case. Much easier. At least I think so. Combine them into one. Is that okay? Yeah. What do we need? So how many integrals does this represent? How many does this represent? An infinite number. We want to isolate it to 1. How do we do that? Yeah, they give us, this is called the initial condition right here. Or not, it's a condition. It doesn't have to be the initial one, but so we know that when x is equal to 6, y is equal to negative 4. So we plug that in, so we get negative 4 squared over 2 equals 3 times 6 minus 36 over 2. So what's that equal to? 8 equals 18 minus 18 plus c. So what does c equal? 8. So what does that tell us the equation is? Y squared over 2 is equal to 3x minus x squared over 2 plus what?
8.
What do we now need to isolate? Y. Y squared is equal to 6x minus x squared plus 16. So y is equal to plus or minus the square root of this. How do we figure out which one we want? We can't use both of them. We need one. We need a function. That's not a function. Hint. When x is 6, y is negative 4. Look at this equation. Which one is it going to be? The positive one or the negative one? When x is 6, y is negative 4. So it's going to be the negative one. The output needs to be negative. So since we need to go through 6, negative 4, we're looking at y equals negative the square root of 6x minus x squared plus 16. Was this much easier than the separation of variables question we did yesterday or 2 days ago? Yeah. This right here, there's no crazy like natural log or absolute value to logic your way through. In this case, it is. Is this about as easy as the integration can be?
Yeah.
Pretty much. It really doesn't get much easier for integration. This right here, you would have gotten 9 points right here if you had done this. 9 points. Are there a lot of ways to miss points? If you don't properly separate the variables, if you don't get to this right here, do you know what score you get? 0 out of 6 on this section. You have to get to there. You get a point just for this. You get a point for getting to this, and then you get a point for the answer. There's 6 points in this one. Stop, guys. The first derivative test is generally harder because you have to take the derivative and then test the value to the left and test the value to the right. Just do. Can you take the derivative of this thing?
Yeah, but it's hard because
E makes it easy. 1 minus 3e to the negative 0.2 root t, right? So let's find the second derivative, p double prime of t. What's that going to be? 0 minus 3e to the negative 0.2 root t times what? Negative 0.2 over we're taking the derivative of this. So what do you drop to the front? A 1/2, so it's over 2 times t to the what power? Negative 1/2, like that. So yeah, you'd have to type that out. You can also do it on your calculator. Did you know you can do derivatives on your calculator? Okay, let's do that. What's the function? Let's do this here. 1 minus 3 e to the what?
negative 0.2 root t.
0.2 second square root of x, like this, right? Watch this. If you go to math, math. You have this on your calculator, n derive right there. The formatting of mine is a little different, but you it'll be, you can do the same thing on your calculator. y1, and what are we doing the second derivative at?
30.174.
What?
30.174.
Yep. There it is. So what does that tell you about the concavity at that x value?
It's concave.
Concave up. Up, so what is it? Min. Okay, now it's asking, is the lake safe when the number of gallons of pollutant is at its minimum? How do you figure that out? Put what back into the equation? The amount of pollutants in the lake, is going to be equal to the initial amount, which is what? 50, plus the integral from 0 to t of the change in pollutants, because this represents the net change in pollutants, right? So you literally write that down, and then you just need to type it into your calculator. You already have it. So look, what do? We do 50 plus math, 50 plus math fn function integrate, and we're going from what? 0 to what?
1 point. Oh.
To what? What time are we at?
30.174.
174.
Is it better round there though?
You shouldn't really, but I don't have it stored, so let's just go with this for now and see how close we are. You're absolutely right, though. Be very careful about rounding before you get to the final answer. And then what do we put in for the function? y1, and it's dx. You press enter. Look at that. So is it safe? It is safe. And you'd literally just write down the answer, and you'd get that full credit right there. So is it safe? Yes. Safe. Cool. How many people did you get this? Anybody get that? No? Do you understand what this says right here? Like if you have the velocity of a car and you want to know where it's at after a time t, you need to know its starting position and the velocity. Did we ever actually find the general antiderivative of the rate of change of the pollutants here? No, we didn't. We don't need to. Did we ever need to integrate it? No, we did a definite integral. Okay, D. D, here we go. An investigator uses the tangent line approximation at P of t at t equals 0 as a model for the amount of pollutant in the lake. At what time t does this model predict that the lake becomes safe? Okay, so you agree that the amount of pollutant in the lake is going down, correct? It's going down at some rate. What it's saying is at time equals 0, how much pollutant is in the lake?
50.
50. So we know that point is 0, comma 50. Agreed? So what it's saying is, if you took the tangent line there, if you took this tangent line, when does that tangent line predict, as a model, at what time does this model predict that the lake becomes safe? We're trying to find when that tangent line crosses what line?
40.
40, exactly. Correct. We're trying to find this time right there. That time. So in order to find that intersection point, what do we need to find first?
The function.
The function. We need to find the equation of the line. Right. We have a point. What's the only other thing we need?
Slope.
The slope. So we need to know what is p prime at
A 0.
0. Exactly. And that's going to be 1 minus 3e to the what?
Negative 0.2
Root 0, right? Do you agree with that? So that's going to be 1 minus 3e to the,
0.
so that's going to be negative what?
2.
2. Close. Negative 2. You got that? So that term will become negative 3. You're correct, yes. So what's the equation of this line? Y minus 50 is equal to negative 2 times x minus 0. And we want to know when y is equal to 40, so we get 40 minus 50 equals negative 2x. So we have negative 10 is equal to negative 2x, so x is equal to what? 5. Great. So the tangent line predicts it'll be at time equals 5. Is that actually going to be accurate?
No.
Why is that so inaccurate in this case?
Because it's steep.
Because what is steep?
The curve.
No.
Tangent.
That's the opposite of what you just said. The tangent line is really short. This curve actually, what's this curve actually going to look like in relation to it? What does it do?
Veers off.
It does this, right? It takes a lot longer for it to cross. I mean, what was it actually? Time equals what? 30.174, right? That was the actual intersection point, but the tangent line here is at 5. So it's decreasing fastest at the beginning, and then it decreases less quickly later. Does that make sense? Which makes sense because it was a concave up. Anyway, okay. Okay.